then I'm sorry. When you just have now. And you can be on your laptop. I'm not going to.
No, I'm okay.
Me too. I will.
Yeah, I know. But then by the time
I'm not going to. I'm getting a little constant. That's why.
It's going to be more costly.
All right, good morning everyone. Welcome to the second day of the workshop. So it's a pleasure to introduce Ben Recht from UC Berkeley, who will give an overview of the state of contemporary computing substrates for optimization methods. And you mentioned the lightning talks as well, right?
We should all mention lightning talks. We still have room for more lightning talks. So if you're interested, please email me with all caps in the title. We've got some really cool ones lined up, but we have room for more. So strongly encourage everybody to who's not speaking in the main program to please send me an email and sign up for a talk. It'll be fun. And those are going to be on Thursday afternoon. Okay. So just like Professor Madri from MIT, I decided to scrap everything I said I was going to talk about, which is fine. I think that's just how this goes. Come on. Oh, clicky thing works. OK, there we go. That's the same thing. All right, good. Now the animations are really ready to go. So we were supposed to give a survey. I started writing the survey, and I got bored. This is the same thing that happened to I mean, I guess this is just what happens. So instead, what I want to talk about is actually a bit more of a personal story than a kind of broad survey, because I think those are easier to motivate. So I'm going to call this my Don Quixote tilting at windmills talk. And I know that everything in iterative algorithms and every kind of workshop I've gone to for the past decade has all been about sublinear algorithms. But what I want to ask in this talk is, have we maybe missed the boat a little bit and forgot about superlinear algorithms? And maybe these are actually possible, even in our big data world. Maybe. And maybe we're actually already running superlinear algorithms and just don't realize it. And so we should be focusing on other things in this space. So this talk was assembled by torturing some graduate students and postdocs to get some content. And they, as usual, had nothing to do with the actual, what I'm going to say has nothing to do with what they intended me to say. So we'll see. There will be a divergence. And all mistakes are mine. Right. So what's the holy grail of optimization? What's the one problem we all want to solve? At the end of the day, it's find an x such that ax equals b. I feel like if we had this primitive, everything would be good, right? This is kind of our universal primitive. Weird, and yeah, no? I don't know. Anyway, why is that? I mean, it's also like kind of like, it is the solution. Solving this problem is also solving the solution of probably the simplest unconstrained optimization problem, the positive definite, or the strongly convex quadratic program. And obviously this is, you can use this primitive to do linear regression and classification. Even though people argue with me, least squares classification is a perfectly fine thing to do. Obviously, to solve interior point methods at large scale, or at any scale, honestly, you have to be solving every iteration requires solving a linear system. And obviously, if we want to use sum squares, we actually want to operationalize this and make this real. We have to be able to solve interior point methods. So as a result, sum of squares also, even though it's polynomials, ends up reducing back to linear equations. And there's all sorts of optimization problems where we actually use quadratic programming as a subroutine, not just in interior point methods, but obviously sequential quadratic programming and Newton's method are two other examples. So it's kind of like this backbone thing. It enables all sorts of stuff. And it's also funny, oddly enough, right, that this problem ends up being like the hardest optimization problem for iterative methods, which is weird. So it's like, we know that this is actually in some sense, if we can understand how to solve this well, we can actually, sometimes hopefully even move to nonlinear problems, either through sequential quadratic programming, Newton's method, or other kind of analogies. OK, so hopefully everybody agrees with me here. Least squares, it's a thing to do. And in particular, what I want to talk today is something that we always kind of punt on, is the dense case, when A has all of the, I'm just not going to assume that there are any non-zeros in A. There could be some, but I really want to talk about the case when this is almost full. And I guess the reason for doing this is that if we could solve the dense case well, we could solve even bigger sparse cases. Maybe, right? No? Is that fair? That just feels right to me. It's so in Lieben's talk yesterday, right? Like there was a reduction to, so you use graph structure to reduce a problem that's very sparse into a smaller dense problem, right? So there's this kind of elimination into a bunch of smaller dense programs. But underneath all of that, you still have dense programs that you have to solve. And if you can make those larger, it even enables larger sparse solvers. Okay? So what I want to just talk about today is solving AX equals B and trying to do that as efficiently as possible. So this is a workshop on iterative solvers. So we start to look at what do iterative solvers do for least squares. The simplest iterative solver I know is the steepest descent method, but there's probably something even simpler. Steepest descent just computes a residual and moves opposite that residual. Do that right? Yes, right? OK, that's steepest descent. And so what's the complexity? Well, this is the number of iterations times the flops per iteration. And the number of iterations goes as like, the Lipschitz, the largest, actually I guess it's positive definite now. So it's just the largest eigenvalue of A divided by the smallest eigenvalue. So it's the condition number times log 1 over epsilon, which is your desired precision. That's basically the number of iterations you have to run. And then per iteration, you have to do matrix vector multiplies. And then some accumulation, so it's about O of n squared, right? So overall, this is an algorithm that takes O of n squared time times some kind of iteration based on how accurate you want to get. Okay. So first thing to note is it is, once we go to the dense case, not a sublinear algorithm, because we always hide in our big O notation the number of non-zeros in A. So if this were to scale somehow linearly, if the number of non-zeros was linear, we'd have a sublinear algorithm. But as soon as you have any reasonable amount of density, this is steepest descent is not a sublinear algorithm. No?
Well, if it comes from a least squares problem, then you use your matrix vector products with A and not the Hessian, right?
What you're saying? So if I have a fast multiply for A, right? Basically, it's the amount of time it takes to do the fast multiply is what you're saying, Mark, right? Sure. So if I have a fast multiply for A, this could be faster, but assuming no extra structure, the amount of time it's going to take is n squared, right? That's a fair point. OK. So what about other iterative solvers? And I was going to do stochastic gradient descent, but I just did coordinate descent, which actually in this case has a different name, right? Coordinate descent has a different name. It's called Gauss-Seidel, and it's kind of something that we would learn in linear algebra class, but they're the exact same algorithm. And in this case, what you do is just one coordinate at a time, which you pick at every iteration, usually at random. You pick a random coordinate, and then you just do this update, which looks like essentially one update of what we would do is steepest descent, and it's renormalized by the diagonal entry in A. Right? And this is the Gauss-Seidel method that people know. So flops per iteration here is less. It's n, because I look at one column at a time. But unfortunately, there's no free lunch here. Then the actual scaling, which I think I got this right, Steve. No? Sorry, I took this from Steve's paper. I think I got this right. So that's why I'm calling him. The actual number of iterations actually now increases. So you actually have to run linearly with n. So at the end of the day, it's almost the same running time as the steepest descent method. The main difference being, of course, that there's a different constant in the numerator. There's something called L max instead of capital L, which is actually related to, in the quadratic case, that's just the maximum magnitude of the diagonal. OK, so this is the maximum magnitude of the diagonal as opposed to the maximum eigenvalue. So it could be better. It could be better. But again, it's still n squared times some structural constant. And in some sense, everything you look at for this problem looks like something like n squared times a structural constant about this matrix, some instance-dependent constant, times log 1 over epsilon. Now how long? So it's not really sublinear in dimension unless you have a fast multiply for A, meaning that either A is sparse or there's some kind of mechanism to multiply A quickly. And I think that the interesting part here is that that to actually just solve this system using, I don't know, a Cholesky factorization, let's say, takes n cubed, O of n cubed operations. So we're playing with a little bit of fire here because this thing we better hope is much less than n, right? We better hope that this number is much less than n. Yes, sir.
Your sublinear means sub n squared?
I don't know what sublinear means, Ravi. Actually, I'm sorry. Let's just I've been attending conferences on sublinearity for a long time. I never know. I think sublinear just means sublinear in whatever number I care about. So it's like if it was n cubed and it's less than n cubed, it's sublinear. It changes this definition from line to line. That's what Piotr told me. So I'm just going to go with what he told me. Sublinear in whatever quantity you care about. So Anyway, for me, usually sublinear means sublinear dimension, though. So I think that's usually what I have, at least in my head, as sublinear in n. But I don't know, to be fair. OK. All right, but the point is that n cubed actually sounds really bad, but when you start comparing it to actually what happens in these dense problems, it's not so bad. And I mean, I'm going to make an analogy that's not clear with least squares, but let's imagine we were doing some kind of neural network training. We've gone to using stochastic gradient descent on something that's very dense. Right? And again, like so it feels linear, but since the size of the networks scales with the number of data points, now we actually have there, it's also a quadratic time algorithm. So jumping from quadratic time to cubic time is a factor of n. It's not 2 factors of n. I think it's just in almost all cases now, trying to get to algorithms that scale as n cubed may be reachable. It's not as big a leap as I think we might have imagined. Everybody seems skeptical. So let me show this to you. Let me show you to you what.
How many parameters are in a typical neural network?
Well, OK, how about this one? N is 60,000. I had Vishal run this last night. Vishal's in the crowd today. Huh?
You're missing like 2 zeros
What?
in your n.
Well, you got to square it to get the number of parameters. That's big. Wait, what are you looking for?
I want
The size of x?
6 million parameters.
Well, the size of x, right? It's 60,000 by 10. So I'm only off by 10 there. That's fine. That's where we're trying to go, Mark. This is good. Stay with me on this. OK, so 60,000 by 10. Here's the thing about 60,000 by 10 is that we could actually do this and on a server, which I will describe which server in a minute, that Vishal ran last night. This took 111 seconds to actually just solve this directly, which is whatever in SciPy doing linalg.solve, 111 seconds. Running block Gauss-Seidel, we ran it for essentially three passes over the matrix. Took 127 seconds. And if you actually compare the relative error between what the direct solve gives you, which I'm calling x star, and what the iterative solve gives you, which I'm calling x, the relative error is 0.58, which is not great. That's not what I would call epsilon. I would call that, that's a big, big epsilon. Usually epsilon has to be less than half, right? In the theory community? OK, anyway, that's big. All right, so it takes even allowing these two things the same amount of time, you're actually not getting a very accurate answer. And the question is, are we selling ourselves short with crummy iterative methods? Because it does seem like that for the same amount of time budget, wall clock, which is what we care about, we can actually get a much higher quality answer doing direct solve. Yes, Pablo?
What about the spectral properties of A? I mean, a lot of these things depend on.
Absolutely, right? What is this K of A? Yeah, so here's one. First of all, we never know. When somebody hands us a matrix A, I never know actually what K of A is. We prove theorems, but actually computing, usually estimating K of A is just as hard as solving the problem.
I mean, it depends on the application.
Yeah, sometimes we know. Sometimes we know, but more often than not. So for this particular case, anybody can probably guess what I was doing here, right? So anyway, for this particular case, this was a problem from machine learning. There's one data set in machine learning that we use as benchmarks. Way too much. But anyway, this is actually, the condition number is horrible. It's a really terribly conditioned problem. Yes?
So I guess this was a classification problem. Did you see a difference in accuracy between the two?
Yes.
Okay.
Yes. So for the end result, that's another thing that actually I don't want to spend too much time on, but this is actually a huge mistake that the machine learning community made. And I talk about this in other talks. The fact that we know that generalization error is going to go as 1 over square root of n, so that means that we can optimize to 1 over square root of n. First of all, we never optimized to 1 over square root of n here, right? We didn't get that close. And second of all, just because you have a sum of 2 terms doesn't mean they have to be equal. Like when you're minimizing a sum of 2 terms, you can set 1 to 0, and the other one might get smaller. So anyway, but that's a longer digression, which I can tell you about. But yes, the classification accuracy is much better for this one. So even on this stupid problem that shall remain nameless. But that's right, dirty secret here. OK, so why is it faster, though, right? Because it's still n squared versus n cubed. One reason could be condition number, which Pablo is suggesting, which is fine. But condition number is really just governing why this accuracy is so slow. Why is it that 3 passes, 3 matrix multiplies, essentially the same amount of flops as 3 matrix multiplies, matrix vector multiplies, is slower than doing a Cholesky? And I think one reason is that to get maximum speed, you have to randomize these methods. And randomization requires data movement, and data movement is slow. And it's something that we don't count in our flop counts unless you're Jim Demo. And so maybe we should be more like Jim. Honestly, counting communication and counting movement is probably just as important as counting flops. And I think that's part of one of the issues here. Because if you start messing with moving things back and forth in your memory, you start to actually lose time. And the second question, this goes back to Mark's point, is that if I actually want to get something bigger, maybe I just need more RAM. Right? So how much RAM do I need for 60,000 by 60,000? Well, OK, it's about 30 gigabytes to store that in double precision. And the solve is 111. And we did this on a machine that has 64 cores and 2 terabytes of RAM. So we have headroom. And in fact, like, we could probably do 350K in 6 hours if we were so inclined. Right? So that's getting bigger. That's getting bigger. But I think, like, there's another number of a data set that shall not be named. Yeah? OK. Anyway, so that's 12 terabytes. That doesn't fit on this machine. And indeed, it will probably, with this machine, even if it did, this extrapolation is just assuming that we get perfect cubic scaling. So doing that extrapolation would take about 10 days, which is a long time. Okay. So superlinear scaling is the worst. So as I try to make these things bigger, it does seem like I will suffer. On the other hand, the memory demand growing quadratically, what does that mean? So I think the biggest machines that are easy to get, that are not ridiculously expensive, have 4 terabytes of RAM. It's hard to get much beyond that at this point. Although 4 terabytes is still 4 times bigger than it was 4 years ago. So memory does seem to at least still be growing, even if processors aren't getting faster. And cubic time scaling means we need a lot of cores, right? So we have problems that we need a lot more memory and we need a lot more cores. But let's say we had a machine that had those. We could probably solve this problem if we can get access to more compute, right? So the question is, where can I get access to this compute, right? And I think also, like, where do I even get access to this compute? And the answer, and I've been dragged kicking and screaming into this regime because I'm not really fond of it, but the answer is always the cloud, right? I mean, that's the Berkeley. Berkeley's been big on this, and so is the Bay Area, and it's it's a big marketing thing, and it's this magical place where there's like all these machines, and you can have all of them. Right? And all of these machines have a ton of RAM in them, right? So you can get all of that RAM too. And the cloud even has like GPUs. So if you don't have a GPU in your house, you can get one on the cloud. It actually has FPGAs now, which I still have not figured out why they're there. I do not. Does anyone know what the use case is for the FPGAs? Amazon has them. Other than, like, I think playing arbitrage against the Amazon market.
Application specific, then often you can do better.
But why would you want it in the cloud?
That I don't.
Okay, so Yelena is saying that, like, a lot of times, I mean, what I know for FPGAs is, like, if you don't want to make a chip, but you want something that's almost as good as making your own chip, you program the FPGA, and you maybe put that on a robot, or you put that on a trading floor, so you can get some high frequency arbitrage advantage.
But, like, what you could do is that if you, like, have a lot of computations to make, you want to maybe design your FPGAs to put that.
So it turns out that actually is the only application I've heard so far that I believe, which is what Alexander said. I will definitely repeat it. It's actually what a lot of people are doing for circuit design is using cloud FPGAs to try out. So I could just get hundreds of these things, try out a bunch of different designs, and see which one is best before I actually go and print it. So that's actually something that folks in the Aspire lab here at Berkeley are definitely doing, and I think this is a common pattern. But I don't know. Anyway, they're there though. So if you guys have something you want to do with FPGAs, they're in the cloud. They're also like unicorns, and they're rainbows, and it's a magical place. So, right? I mean, there's a lot of marketing that goes into the cloud. But I think having spent a few years with everybody kind of working on this stuff, it's a little bit daunting to get into the cloud because you go and you start to look at, like, what was available, and it's just like a lot more than. It's a lot more than just like one random GPU, right? You have all these instance types. You have different providers that have all these different things. And there's this great website. I love this website, ec2instances.info. And it lists all the possible things you can get on the particular region on AWS. And yeah, I don't know what you do. It's like going to the Whole Foods. It's like you just got all this great options, and it's kind of hard to figure out what's the right thing for my problem. So usually when you go, and it used to be you just go, like, you go to the Apple store and you just max all the buttons, and then that's the computer you buy, right? But it's unfortunately not that clear in the cloud that that's the right thing to do. So that's an Eric Jonas quote, so I'm just gonna put that in there. That's his hashtag. Please attribute appropriately that the cloud is too damn hard. It is really hard. It's not as simple as just going and, like, treating it. I mean, you can just get single boxes, like this 2 terabyte machine that Vaishal got yesterday, and then treat it like a Unix box. But even that interface is not as standard as it should be. And, like, I have no idea what we're gonna actually what the right thing is to get. And I think the more important question is these things cost money constantly, right? They're not free. They're not free. So it's very easy. Again, I'm not going to name names here. Very, very easy to burn through all of the kind of Amazon grants that you get in a weekend if you're not careful. And so what do you do? And again, yeah, I don't know. It's a bit of chaos. So here, let me show you something crazy. Yes.
I have another basic question. How do you verify that they gave you what you paid for? They gave you that much RAM.
Type HTOF, I guess, is what you typically do. It's a good thing. Where do these contracts come from? How do we trust them? How do you even know that they gave you the cores in the same machine? You guys have an answer?
I mean, it's actually an issue that the tenancy situation is sometimes complicated,
Yes.
right? Like this hardware is being multiplexed to various hypervisors with other providers. So sometimes when you actually go through and benchmark, you'll discover that, this Xeon machine, if you had it under your desk, would give you this performance. And when you run it on AWS, you only get this performance.
That's right. So the answer is you don't necessarily. So again, that's a whole other issue of actually what are you actually getting? That's a good question. But for the buck, that 2 terabyte machine or whatever, 2 terabyte virtual machine costs $2 an hour, which is nice if you just need to run like 2 or 3 MNIST demos. That's fine. For more than that, maybe you have to think a little harder.
I don't know if you're done with iterative solvers, but going back to the spectral question, if you have a dense matrix of enormous size and has 2 distinct eigenvalues,
Yeah.
you can solve it in 2 iterations.
Sure.
Conjugate gradients.
Do you have that instance?
And all the problems that I know, including neural networks,
Yeah.
especially neural networks, have a lot of 0 eigenvalues. So there's a distribution of eigenvalues. It's not going to give.
I mean, you didn't believe my experiment?
You're writing the worst case.
No, I ran a random kernel ridge regression problem. Sorry, I respectfully disagree. I never have seen conjugate gradient actually converge again, we need conjugate gradient to converge in 3 iterations to be competitive with direct solve.
Okay, sure, talk, I won't say.
But I'm just saying, we need to converge in 3 iterations.
Yeah.
And it does not.
So I'm just saying, if it has 3 eigenvalues, it converges in 3 iterations.
But no problems that I've ever encountered have 3 eigenvalues. So it'll be fine, but none of the problems that I care about have 3 eigenvalues. So
this is with no preconditioners.
Yes, it's also with no preconditioner. Yeah.
So,
Oh, we've tried that. We can talk. We'll talk. We'll talk.
I realize you're talking to people who've been using conjugate gradients for 30 years.
Sure.
In all sorts of areas.
Sure.
Fluids and this and
Sure.
so on. Not exactly 3-0 eigenvalues, but small number of, distribution of eigenvalues versus sharp drop and a very different behavior than the worst case behavior of steepest descent, right? Steepest descent always has the worst case behavior, right?
Sure.
So you're giving us worst case behavior of things. That's just the only thing I was going to say. Yeah, people do conjugate gradients and multi.
I mean, you guys could run whatever you'd like. I'm just saying, wouldn't it be nice if you could just do a direct solve? Because then you don't have to worry. Then I don't have to worry about what the eigenvalue structure is. Again, it's just n cubed. There's no instance dependency. Wouldn't that be nice? Yes. Okay, so now we're moving on. That would be nice. All right. So, but then it's instance dependent.
no.
Oh, come on, Ken. Well, how do you know?
Well,
I mean, again, it depends on being able to actually get that gap small.
yeah, but for least squares at least, the preconditioners can be such that you have an extremely well-conditioned problem. Right.
Yes, but again, it depends on the instance.
No,
How can it not?
because for least squares.
Yes.
Okay, so where you do an approximate QR decomposition and then use that approximate QR decomposition. Not for the general case of PSD,
Sure.
but for least squares.
Sure. Anyway, I'm not. This is fine. We could. I mean, you guys could use preconditioners too. Again, yes, Ravi.
Yeah, sorry for that. Not being an insider, where are we going? Are there equation solvers already in the cloud, or are you going to tell us how to do that? Or
Yeah.
Okay, good. You're going to tell us.
Yeah.
Okay, good.
Absolutely. Absolutely. The problem is there's okay, we have this tyranny of choice. We have the same thing in optimization. We have the exact same thing in optimization. There are 1,000 papers a day on some new little tweak of coordinate descent, or on ADMM, or on non-convex this. And they propose 17 different things you could do, or preconditioners. And there are lots of things you can do. There are lots of things you could do. I see no papers telling me how to solve these squares, just exactly. Because maybe that's a solved problem and not that interesting, but I would like to be able to do it. It's a nice benchmark. Again, like I can get this, I'm going to go back here. I would like to be able to actually just compute this number sometimes. And so that needs this x squared, x star. Right? So I actually think that there is a difference, there is a value, and like we can have, like the tyranny of choice does not end with just the cloud. Right? This is already a problem. But I do think that practitioners, you guys, what algorithm do you use? And the same thing goes with neural nets. What algorithm do I use? So there are lots of tyranny of choice. Let's prune ourselves today. I'm going to just talk about one, which is I would like to be able to do direct solve. And then we can, that's hopefully, that only fixes one thing, which is the optimization problem. I still have to figure out how to actually now do it, which is another thing. So let me show you why that's also not easy. Okay? This is here are, we're just going to look at a QR factorization, an exact QR factorization that we're going to do it by a tall skinny method. Okay? And what we have here is 5 different configurations that all have the same hourly cost. Okay? And so this is again, they're color barred. This is the time in seconds it takes for the exact same hourly cost. So we have 5 different, the same cost, and we're getting a factor of 2 difference in time. And we also get, I mean, it's actually kind of obvious what's happening here. Memory bandwidth is actually the important thing. Okay? And so there's a 2x performance difference for the exact same price, which is a bit disturbing, right? So how do you actually pick that, right? So these choices actually really matter because even though you have like some ideal benchmark to get, if you pick something badly, you can actually have a fairly large gap in your accuracy as well. So I'm going to just skip this because it's going to, OK. Let me just say, let's see where we go here. Okay. So one thing that we're actually able to do, I'm skipping it because I'm almost out of time, but I wanted to get to something else, is that actually Shivram, who is now at Microsoft Research and will be at the University of Wisconsin, not Washington, sorry, Steve. Brain fart, following Microsoft, actually has a really nice paper showing that you can actually predict doing small instances how these things will work on large instances. And this is just simple experiment design where you do small instances and try to extrapolate. So by running essentially, let's see if we can, where's that bar? That's pot. By running very small benchmarks, you can actually able to you can actually pretty accurately predict how long the running time will actually take on the big instances, and the training time for these things is very small. So there's a big gap between actually, so you just run small little benchmarks that extrapolates out to large things. But again, even here, right? I think the point is that there's lots of choices, and these choices kind of matter, and I would prefer that they get hidden from me. And also, I didn't tell us about RAM yet. This is just about bandwidth and configuration selection, and we'd like to actually skip all of that. So for that, I want to talk about something that we've been using in the group, and this is all Eric's fault. So again, the remainder of the talk is all Eric's fault. There's this funny thing that Amazon has started supporting, which is called LAMBDA, right? Which apparently makes our lives easy. That's what the infographic tells me. So what does LAMBDA do? Just like we think with Lambda calculus, it just executes functions for us. And it's essentially these stateless, serverless functions. I tell Amazon, execute this function. It executes it and puts the result in this S3 bucket. And what's S3? S3 is actually the part that I'm most interested in. It's something called the simple storage service. And it's essentially just infinite RAM that they charge you money to keep occupied. So I'll talk about the money there in a second. All right? But what's interesting is got to this weird blob storage, you have 600 megabytes per second per machine. Which is the same speed as serial ATA. It's a little bit slower than a PCI bus. Okay. But I get that per machine. I can get lots of machines. Okay. And again, the big thing that I was trying to show in that previous plot was memory bandwidth. It's kind of the thing that you want to maximize. You want to have lots of cores with maximal memory bandwidth. So Eric, over a weekend, decided to build something which was essentially just, instead of executing one of these guys, would just basically overwrite Python map such that it would map to lots of Lambda instances. And what does that do? So this is actually, I think, the part where it starts to get a little weird and interesting, is that you could get, if you ask Amazon nicely, 3,000, 10,000 simultaneous function executions on 10,000 different cores. Right? These little tiny flock of cores. And their aggregate teraflops at about 3,000 workers is 45 teraflops, which is like 10 GPUs. That's like 10 P100s, which is pretty cool. Okay, and also the aggregate bandwidth to the S3 is approaching about 80 gigabytes per second, which is pretty nice. It's pretty fast. So I was kind of shocked by these numbers. That's pretty nuts. Just doing a bunch of microservices, you can get some teraflops. And so he built this thing called TYRANN because it was supposed to be a flock of condors, I think is the idea. If everybody remembers Condor, some people. Anyway, if you don't, it's probably for the best. But I like to antagonize Marone, but he's not here. Anyway, so but TYRANN is supposed to be kind of like these little guys. They all flock out and they do their jobs for you. And it combines Python. I mean, you just write native Python, and again, you overwrite map. So this just allows you to kind of do simple map, but it does simple map. It executes this thing in the cloud. And the way it works, which is kind of funny, is you write some crap on your laptop. It will serialize this and puts it up in this storage. Then you invoke LAMBDA, and then LAMBDA just does magic stuff where it pulls this stuff, runs the code. You ask for the result, and eventually this ends up in S3, and you get it back. What's funny is you just write crap on your laptop. And I never actually have to worry about picking a server, which is actually now ShivRAM can do all this stuff behind the scenes. And I have, this is now I feel like I'm a systems person. I have an abstraction boundary. Yes, so everything behind the scenes you never have to worry about. And the kinds of stuff that we can actually do is just thinking about how do we actually use map to try to do numerical computation. Hey, I should have actually had a cloud here. Anyway, OK, so now this actually lets us ask some weird and crazy things. Okay, so remember, all I wanted was more RAM. And the question is, how expensive is this blob storage S3? It's essentially infinite RAM. It does. I don't know how much RAM is in S3. I'm just going to assume we haven't hit the limit yet. We haven't hit the limit yet. Because the problem is that they just start charging you money. But it's a little funny. The first 50 terabytes per month is 0.023 cents per dollars, $0.023 per gigabyte. And if you have over 5, it goes down the more you store. So it's like this is the beautiful part of infinity. The more you store, the less they charge you. Wait, not exactly. Not exactly. So here, let me ask you a question. How much can I get for $1? Another one of my favorite slides that Eric has ever made here. There we go. This plot blew my mind. Completely blew my mind. This is how much storage you can get for $1. So remember, they're charging you by the amount of time you occupy it. So for 1 minute, I can get 2 petabytes for $1. That's insane. That's insane. Now there's a problem. Who sees the problem with this?
Everyone wants one.
Huh? Well, I mean, like it still takes a little while. I mean, unless this is a 3 iterations of conjugate gradient, I'm gonna be in trouble. It's gonna take longer than this. And actually, I can't write to it that fast. That was the other plot that we had showed a few slides ago. So it's kind of superimposing our current LAMBDA capabilities on top of this. So the amount of time it takes to read and write to this memory is too slow to actually get a petabyte in, and then to delete it. Because again, if you keep that for 2 minutes, that's $2, and eventually that starts to add up. But there's this interesting regime right here at the 100 terabyte regime, where we can actually actively treat this as 100 terabytes of RAM that hopefully at the end you remember to delete, right? Okay, I've got some people here who have to remember delete. Because if you leave it for a day, we get in trouble. Anyway, but this is an interesting line. So how do your algorithm, this is actually, I think this is like the open problem of this, is do your algorithms change if you have infinite memory, but it comes at a limited rate? And I don't know the answer to that. Could be iterative too. Let's not, do your iterative algorithms change if I have infinite memory, but it comes at a limited rate? Right. And it's kind of this, so we had that on the previous slide, right? This is the beyond P space. What if that part doesn't matter? And I think we know that algorithms do change if we don't have to consider that kind of memory requirement. So let me close by trying to say how we do linear algebra. Okay, and we're calling this numpywren, which I don't like the name, but that's fine. Everybody, sorry, I'm just announcing it. It's too long. Numpywren. Anyway, so something that's hopefully everybody knows is that actually to do a matrix multiply that looks like this, where I have long times tall, is one of these really trivial things to do in MapReduce. So this is kind of one of the standard examples that people have in MapReduce. Because what I do is I just partition this guy into blocks and this guy into blocks. Every worker gets those and then reduces the sum. Right? So that's kind of a standard thing to do in a MapReduce framework. But there's other things that are actually a little bit harder to do, that are actually primitives that we need to do, at least to do a Cholesky factorization, which is where I'm going to close, is that you actually kind of have to do like large rank updates. So you have, low rank updates, where I have to actually form a low rank matrix and add it to a big matrix. Okay, so this is really hard to store in memory, so it's hard to do with single workers. And 8 terabytes in memory, even for a traditional cluster, is a pain in the butt. Even though the max single node we can get is 4 terabytes. And how much are the 4 terabyte machines?
Something like 14 to 20 bucks an hour. Yeah.
So 2 terabyte, but this is actually where this is interesting. I know that this week has been a lot of memory, remembrances of Michael Cohen, but the last conversation I had with Michael was actually about this stuff. And he was asking, where has it become nonlinear in terms of memory? And actually the interesting question is that, I mean, as everybody knows now, Michael was interested in everything. So when does this become nonlinear in terms of memory? And it's about at that 4 gigabyte regime. So 2 terabytes, thank you. So 2 terabyte machine I can get for $2 an hour. 4 terabytes is costing maybe $20 an hour. So you're kind of pushing it up there, and it's also expensive if you try it. Anytime I have to build a cluster, it's really annoying. So what if I treat this thing, this kind of S3 thing, as RAM? And what would you do? So what we could do is use S3 to store the matrices, and then use the lambdas to kind of operate on each of these blocks, right? And output everything in parallel using this shared RAM disk. And I think these are old numbers. Vaishal's actually gotten this a little bit faster. That's Vaishal. And so for these kind of 1.2 million dimensional problems, which Mark was asking me about, you can actually do in less than an hour, you can actually do these kind of, take a low rank matrix, do the outer product, stick it in S3. Okay, at fairly fast rates. Okay, good. So this gets to the end. How do we do Cholesky? Does everybody remember how to do Cholesky? Okay, good. So we want to have a factorization that looks like this. And I'm going to do it by blocks, where let's just say we're going to do a block Cholesky. I want to actually make this factorization so L22 is much bigger than L11. This is a little tiny little block. This is a huge block. Okay, so that's the partitioning. So how do you actually go about doing that? Well, the first thing you do is you take that first block, and then you take a Cholesky factorization of that. That's easy. You can do that. I mean, that you can do on your cell phone. But I don't think there are cell phones in the cloud. Maybe there are. Anyway. And then the nice part is that this part is free. I get to zero that out. So how do I do the next updates? Well, this first column is just simply I can just broadcast the L11 and multiply it by the every guy. So that actually looks much more like a MapReduce thing, but it's trivial to also do it in this kind of TYRANN framework. And then this thing is the interesting case, because that is this low rank update. Right? So the low rank update is A22 minus these L12 transpose blocks. Okay? And so each of these guys get hit. We can do that one in parallel. And that allows us to actually do the Cholesky. OK, so I'm going to stop there. And so Jorge and I have time to fight. I think that there's something interesting here. Whether or not actually it's direct or iterative. The fact that the cloud actually opens up these potentials of having very kind of unusual. I mean, they're not unusual if you were doing parallel computing in the 90s, so I'll be fair. Like having this 2-layer cache, but where the memory layer is infinite is very interesting. So I actually do think there's interesting stuff that can happen if we can actually implement and make open source these kind of like simple linear algebra tools that people can use through Python. For example, we can actually start to run big sums of squares programs, which we're currently memory limited by. And similarly, like a lot of these kind of interior point methods, I think we can start to prototype at a larger scale. I think there's interesting things that we can even do in the sparse case, which I didn't discuss today, because I was only focusing on dense, because it's a little bit easier to think about. But then we can even do it at a larger scale when we start to move to incorporate sparsity. And I think that there are fun and weird algorithmic challenges in this kind of, not only in non-iterative methods, but in this funny model for infinite RAM that I would love to talk to any of you guys about at any time. Okay, so thanks. Yeah, Ken, go ahead.
Processor failure ever come up here?
Processor
failure?
No, actually, that's what's very odd is that a lot of MapReduce was initially designed for things that died. There's definitely straggler effects And I guess occasionally you will get processor failures. But the nice thing about Lambdas is that because you're not actually loading a server, if it dies, you could just ask for it again. There's certain idempotency. So if something's and they've built in straggler mitigation into the TYRANNY interface. So, but I think that it's funny. Like MapReduce was built to be very, very fault tolerant, probably to a fault. It's always hard to actually know how much fault tolerance you need. Unfortunately, it's hard to know how much fault tolerance you need until you really need it. So this is all about how conservative, right? Yeah. This is how conservative you need to be. No, okay, he's good. Jorge's good.
So,
Yeah,
so do you have an examples where you have like, let's say, a million by a million matrix which is dense, that is like coming from some application?
Yeah, so that's a good question. So Kim Chuan doesn't know. I have numbers that were like machine learning dog whistles in here. So I don't know if everybody. So I think maybe not everybody gets those. But okay. So one machine learning dog whistle was at 60,000. That's the size of the MNIST data set. This 1.2 million number is the size of the ImageNet data set, which is kind of this big one in computer vision. This is like was the thing that made deep learning a thing, was that data set. And so you just want to say, if you actually want to use that, that's where I got that 1.2 million number. There are speech data sets that have 20 million examples. So most of the things I have are coming from machine learning. But an easy way to generate large instances for least squares is to try to work your way up the Lasserre hierarchy. So, I mean,
in the case of
right?
in the case of the SOS,
yeah,
the matrix A have very nice structures, and also forming the matrix A is actually the most important, the most time-consuming part. It's not actually solving the linear systems.
But that should be in our advantage here, yes? Because what are you limited by? That's great. Actually, I think that's great. So what are you limited by? You're limited by RAM. That's one thing. And then you're limited by forming A, which can be done in parallel sometimes, right? And so those two. So if I can do a sparse solver at the end, that's great. Yeah.
I think I missed something very basic from the motivation, which is why weren't you looking at accuracy in the A norm, which is kind of standard?
I should have written accuracy in the A norm. That would have been fine. It would not have been better, but I should have written it that way. I didn't. We just did.
It wouldn't be. You're saying you have checked it. It's not any better.
No. I just mostly, actually, the thing I really care about, which is stupid because I do too much machine learning, is out of sample prediction on the test set, right? That's the only thing you really care about. You never care about A norm accuracy. Sorry, again, that's a terrible joke. I'm just saying it because I have two friends from Google here in the front row. So we don't see, it's not significantly better if you look in the A norm. Again, it's just really to get to the kind of precision that you want, which is even 10 to the minus 3 in the A norm, requires tens of passes with the kind of matrices we've been looking at. I agree with Jorge. There are instances which actually will be solved faster by doing, that conjugate gradient will solve more quickly than this. But again, like if I'm allowed myself 20 conjugate gradient iterations as my upper bound, that's when the direct solve becomes competitive.
Do you need more than 20 passes through the data to hit your optimal out-of-sample complexity?
On MNIST?
Sure.
Yes.
Do you need more than n passes?
Probably not, but I haven't got, that's n is 60,000, man. So.
I thought each pass was an n squared operation.
Yeah.
You're comparing to n cubed. So for the iterative to be slower, you need to do n passes.
No, because it's assuming that complexity term is assuming that the condition number is a constant. So asymptotically, it's true.
Yeah.
I just like.
Let's say we do n passes through the data.
Yeah.
Then that would give me an n cubed runtime. I think your gain is actually coming from building the matrix in parallel.
Well, no, it was just in the solve. It wasn't the. It's that we require less data movement. Because even to do the n passes, well, conjugate gradient doesn't require this, but conjugate gradient to converge requires. I mean, it's always less than n. But sometimes it requires hundreds of matrix vector multiplies. For the randomized methods, it requires a data permutation, and that's always.
So what the people do in practice is they just do 2 permutations and alternate between them.
That's right. That's right. That's right. That's right. But then you have to analyze that one. Actually, so one thing I didn't mention, and I guess that we should take a break, so I'll take this as the last question. One thing I didn't mention is actually even 2 permutations is significantly slower than just doing pure with replacement sampling for coordinate descent. When you have block coordinate descent, you really want to be able to every time take a fresh sample. There's a nice paper. We were surprised by this, but breaking locality actually gives you a significant win in both standard Gauss-Seidel and accelerated Gauss-Seidel.
So your motivation for doing this, Ben, is to do exact Newton methods? Or?
Exact Newton methods, even just least squares classification.
But in the nonlinear case, you're thinking about doing exact Newton methods?
Yeah, and actually I'm interested in interior point methods.
All right, let's thank Ben.